Episode: Profiling Harnesses, Network Handlers. Test and profiling harnesses, event handlers, and networking. In this episode, let's talk about another techie topic. Let's talk about test and profiling harnesses and ways to optimize networking code. All of the above optimizing techniques are useless without knowing your targets and your goals. You need to know what your baseline is and where you want to go. What memory storage and performance is expected or required for the holistic experience or for any specific area or function. What network or cloud operation performance and storage is expected. What concurrency and semaphore stalls might exist, and what is the maximum acceptable stall? Are there underutilized processors that should have something operating in them? Just like profiling gives an initial baseline, profiling also provides continuous snapshots and insight on how the product is performing and improving. Continuously monitor. Using automated profiling, ideally, you can track profiles over time to see how areas are trending, ideally improving, or unfortunately worsening. Use automated testing and use test and performance harnesses and use test bots wherever possible. Use automated testing with bots. Use recorded play or key gamepad network inputs for playback. Use scriptable performance and test harnesses. Forcible, arbitrary lags and semaphore stalls in high processing dense areas, like in a racing game, driving through an urban area, can expose great problems in software. So you can create problems in a test harness in order to expose problems that might exist in the real world, but maybe you do not have the ability to otherwise replicate locally. You should look to exercise low and high performance areas in your software, specifically to look for spikes and how you might recover from them. You should look to force extreme load conditions to see how your software will recover from them and not stall or outright soft lock like a crash. As a reminder, focus optimization first on data and then on code. Focus on high time, high frequency functions and algorithms. When optimizing real-time actions over a network, especially over the internet, latency, lag, packet loss, misordered packets, and outright completely lost data packets that will never be found or seen from network transit. They're all things that are critical to the performance of your software and its ability to operate. Network performance problems can be huge, massive problems for your software. Of course, be able to recover from lost or extremely late or damaged data packets. You do not want to have any kind of soft lock or bizarre stalls for the user. Also, you might consider a separate network send-receive packet manager to minimize network transmission and reception delays. But also consider local client software solutions that might hide lag so that lag is not visible to the user. You could just show some kind of loading bar or loading spinner, but that just tells the user shut up and wait. You could implement anticipatory client activity that is corrected whenever the remote server arbitrates and tells the client what really happened. In weird cases, things might pop if the anticipated client behavior activity does not match what the server's decided activity was. But even in popping situations, at least all customers will perceive the same thing, mostly, even if they're playing in the same sandbox. An example of anticipatory activity might be dead reckoning prediction of a vehicle driving down a game's road, while the player turns left, but the server did not relay it until later. And so the vehicle pops back into the position later than when it had turned left. It will still turn left, it's just later. The concept is to make client software arbitrate low-impact actions while the server arbitrates high-impact actions. And the client predicts and plays out its local impact actions, though it is corrected by the server, even if they were high impact. Techniques to correct mismatched client and server states often include not just popping, but fast forwarding, rewinding, teleporting, even blending if the animation or motion is close. For example, you might only have to slightly speed up a run to compensate for a character that should have arrived half a second earlier. There is one universal truth for performance programming on any network or cloud. Polling, listening, waiting for something to happen is inefficient. Literally, the code is just sitting there, spinning in circles, burning cycles in wait that some variable or some state will be set. The code does nothing but wait until something else has happened. But microprocessors don't sit dormant. They spin in cycles, they run in loops, waiting, listening. Reacting to messages via an event handler is much more efficient. Code can do anything it wants, while network packets arrive and are queued for processing. And when a message comes in, like a telephone, only then does it have to answer the telephone. Otherwise, the message handler simply stores the messages that it receives or is planned to send for future processing, when the local software is available and ready to process and do it. And thus, it is virtually never stalled, sitting around doing nothing. The bottom line: write event handlers to process incoming messages and parse them in batches when they are ready, allowing the execution of other local operations while awaiting all the messages to arrive. Avoid writing code that loops, just waiting for a message or an input or an external command to arrive. On the internet, UDP is a very popular communication protocol, likely because it is very fast. However, it does not guarantee that it will ever arrive. UDP delivery packets are not guaranteed to ever be delivered to their recipient over the internet. They are also not guaranteed to be ordered in the same order that they were sent. You have to assume UDP packets are randomly ordered. TCP, on the other hand, which is the most popular communication underlying protocol on the internet, likely because it guarantees the data packets will arrive at its destination and they will be in the order in which they were sent. Games typically create their own reliable UDP system, making a more efficient TCP Lite that is tailored to specific game requirements. Well, that's just another area to optimize. UDP is much faster, even with client software ordering and resend overhead. Use TCP when network speed does not matter. Otherwise, when internet speed does matter, use UDP, but make a reliable UDP system. Well, with all of that techno-babble, I thank you for sifting through it all for some gold optimization nuggets with me. I hope there was a nugget in there, in test and profile harnesses, in event handlers, in networking optimization, etc. I hope a nugget has found its way into your toolbox.